Hey guys, I was in a meeting. I was tied up. Sorry about that. I'm just starting in right now. Thank you for waiting here. Let me share my screen so we have. One, screen 3. All right, so today I wanted to basically talk about the implementation of failure theory in the CLT code. Where's my? Can you guys see my slides? Am I sharing the right screen?
Yeah.
Okay, thank you. Specifically, I wanted to talk about this criteria here. One of them is maximum stress failure theory. This is the first one. The second one I want to talk about is how to implement the Tsai-Wu. This one, Tsai-Wu failure criteria. So let's quickly review what they are. So basically, for each lamina, you're given a set of properties, which usually came from test. For this case, you have fiber direction, compression, tension strength, the first two numbers, matrix direction, compression, tension, and shear strength. Okay, these are the input to the failure criteria. When you do the maximum shear stress theory, you just basically compare your fiber stress, actual stress with these two numbers. Is the tensile stress greater than 1500 megapascal? Is the compressive stress greater than negative 1250? You basically compare, excuse me, the stress to the threshold. Then you apply, you figure out the second matrix direction stress. You compare to these numbers, then you calculate shear stress compared to these numbers. It's tedious, but the good thing is you can identify which stress is violated, and you can possibly get a failure mode determined that way. Okay, so that is you basically comparing the stress you calculated with these thresholds. The Tsai-Wu is overall the better performance criteria among all these things. So Tsai-Wu criteria look like this. It's a interactive theory, so everything that mixed together, you basically calculate a mixture of things. You multiply stress with coefficient, you add them up, you compare that to 1, basically. This is talk about how do you figure out the coefficient of these polynomials when you apply, this is failure envelope. This equation describes the failure envelope. And you can use experimental data. This F1T here is just this number. F1T is one direction tensile stress in the fiber direction, which is some people call X1T. Is a sigma 1T in this case, or X1T. We're talking about the same thing here, basically. All right, and you can calculate all these coefficients using the data. So F1 equals this, F11, F2, F22, F3, and all those things. F12, you had to solve this equation to get F12. And then once you figure that out, you can apply it in this way. You have sigma 1, sigma 2, tau 1, 2 calculated for each lamina. You plug those numbers, multiply with the coefficient, and then you figure out, you compare this to 1. For safe situation, the sum is less than 1. For when this sum is closer to 1, you're in getting to a critical situation. You're near the failure boundaries. When it's greater than 1, it's already failed. Basically, it's already past the failure threshold. All right, so let me show you the code. The code that I used. This is my code. Okay. So this part has to do with failure theory. Okay. This is the input to the failure theory. This is the lamina strength, fiber direction, tension, compression, matrix direction, tension, compression, shear strength. Okay, and this is a Tsai-Wu parameter I calculated. I calculated Tsai-Wu parameter using these set of equations. These set equations, I calculate, leave that there. Okay. All right. Now with this thing, I can now calculate the failure likelihood of a lamina for any lamina. So I started with I poke up, I just make up a lamina layup and then thickness. Each lamina has certain properties. This is a layer 1. This is basically layer 1. Everything's layer 1 here. Put it. And you have layer 2 and 3. Everything is in the vertical column. So my CLT code basically is just like your code. I calculated the stress in the material coordinates, which is here. This is my stress right here. You should already have this code written up by now. So you do all these ABD building, inversion, and solving coordinate transformation. You would have this. For each layer, I calculate the stress at the top of the layer and stress at the bottom layer. And this is my fiber stress, fiber direction stress. It turned out to be tension, positive tension. And then the matrix direction is also tension in this case. And then the shear stress is positive. This is at the bottom of the layer, the 3 number. All right, so with this, I can apply my Psi Wu. Psi Wu has 6 terms. 6 terms, so 1, 2, 3, 4, 5, 6. 6 term right here, this equation, 6 terms. So I calculated each term separately. This is my first term, second term, third, 4, 5, 6. My S1 is the sigma 1 is this number. S2 is sigma 2 is this number. S12 is the shear stress, this number. So I multiply the coefficient with the stress and calculate each term. Then this is the sum of all the terms. Okay. As you can see in this case, this ply already hit the threshold. It went over 1. That means already failed. Okay. So that's my critical ply. And I did this for all the plies. I can see that this ply and this ply is at risk, right? Very high failure indices, okay? And the other plies are still okay. They're way under, okay? Now that's the purpose of the failure criteria. You can identify which ply is your critical ply gonna fail first. And if you know the failure mode, we can do the property reduction and calculate the stress redistribution. Remember that? We'll try that a little later. Okay. Now I'm gonna talk about, is there any question about Psi Wu here? Any, you can type in chat window, whatever that you can. So no more question. I'm gonna talk about the other failure theory. We can put in the CLT code. The other one is the basically the maximum stress theory. So I put the second failure theory over here. This is my block that calculate the failure theory based on the maximum stress. Okay. So I just simply compare. If I look at how I calculate it, I calculate a ratio, which is over here. This ratio. This ratio is just stress. This number, if I highlight it over here. Okay. It's this number, x1 direction tensile stress divided by the 1 direction tensile stress. I calculate this divided by this. If this number is greater than 1, that means it's safe. That means your strength is much higher than the stress. Greater than 1 is higher, okay? So I do this for other failure mode. I do this for, I do this for compression, 2 direct tension, 2 direct compression, and then tau 1, 2. Basically, among these ratios, the smallest one is the failure mode that would likely occur. That's where you get closer to the threshold. The smaller the number, the closer it is to the failure threshold. There is a little bit trick here because it has to do with signs. For example, if the fiber direction is in tensile stress, I would use the if statement to guess. If this number is is tensile stress, the compression is not an issue. So I gave an arbitrary big number. That means it's not an issue. If this number is tension, then the compression threshold become huge number. That means it's safe. Okay. I do the same thing for the first threshold. If the stress is compressive and negative, then the tensile stress will not be the failure mode. Yeah, I gave it that pretty high number here. And then at the end of the box, I calculate the smallest among them all. The smallest number of these ratio is the mode that will, get close to the failure. Okay. It turned out in this case, the smallest number is tensile. This is the smallest number. So by this, I would make the guess that this is a fiber failure. This is X1T closer to its threshold. All right, there's a question on the Cai Wu is not required for Monday. For Monday, you're required to be able to calculate stress. The calculate the you basically the homework one. If you can do homework one with your code, you're fine. Okay. This is for continued improvement in CLT for the remaining of the class, not for Monday. Any question about this? So basically, once you figure out the stress in the material, remember we are using stress in the material direction, okay, not in the global coordinates, 1, 2 direction. All these formulation, all this equation given here is the material coordinates. You got to transfer back to the material coordinates in order to use this equation right here, okay? All right. I'm gonna do a calculation that basically sort of simulate the stress redistribution process that we discussed in last lecture. So I will basically use the same sheets. I can apply a load. Let's say I apply a biaxial stress. So I apply 4E6. All right. That's pretty high. Reduce that 1E6. Okay. All right, so this is pretty low load. So all my 6 layers, it is based on Cai Wu, it's pretty low stress compared to the capacity. Okay. But I can still see that layer 1 and layer 6 is at pretty high load. Okay. Then I can scale this up to certain threshold. Let me try 2.56. All right, let me try to scale up a little bit. 3.16. So let's do a factors here. This is a scaling factor. Alpha. Let's call L. 1E6 multiply this number. I'll just make a way to like easily scale it. I'll scale it twice. And 3 times. Uh, 2.5. Bingo, that's very close now. So now I have a failure. So basically what I did, I simulated, I load this tension XY direction proportionally. At this low threshold, what I do is I have a failure here. This is the failure here, okay. And I want to determine what kind of failure mode it is. Let me look at this number. So this is actually 2-direction tensile failure. See, the 2-direction is hitting this, is the lowest number. Okay. All right, so this will give me a load level that's induced the first ply cracking in 2 directions. Okay, then I will save this. I can, the way I do it, I can copy this thing, copy the whole thing. Let's rename this. I call it second step. That's first step loading. Like second step. This I can copy the whole thing over. This is this first spreadsheet remembered the threshold when the first ply cracking occurred. Then I copy that over here. I calculate. At this point, I would apply the reduction. The reduction is you effectively simulate the damage due to the 2-direction tensile stress cracking. You basically reduces your stresses. Okay. Anybody remember how the ply property was reduced if you have matrix cracking? What do we do? What's the recommended reduction? You basically reduce your matrix controlled property by what is 75%, and fiber controlled property remains the same, right? All right, so let's see. I have, in this case, ply 1 and 6 hitting the same threshold, use similar matrix direction tension. What I do is I go to the layer 1. I reduce this to the 20% of it, 0.25. I reduce this to 20% of it, 25% of it. And I reduce this to 20%, 25% of it. And I reduce this to okay. So what it does, effectively, when you do this, in my case, my code recalculate everything automatically. It immediately redistribute the load. Load distribution different now. Then I can go see my failure criteria. Okay. Now remember, I didn't dial the load down. The load has remained the same. The load still the same load, the same load. This is biaxial tension, right? Now you look at the failure criteria. You see, this used to be 1. This is 1. This is the 1. Now it's become 0.3. It's much safer now. This is because the load was shed from this layer to other layers. Other layer get higher load. This layer get lower load. All right. Now, if you remember the stress strain curve, if you do the test in the lab, this is where the first kink will occur. It'll crack, load redistribute, load carried by other layers, and then you can keep applying load. Okay, let me bring the slides out. All right, so what you're seeing here is this kink here. Due to cracking of certain layers, the stress redistribute, you basically the material will actually show a different modulus, and then you can keep loading it. And when I copy the spreadsheet from from stage 1 to stage 2, step 2, is at this turning point, basically, where the first threshold, when the high Wu is triggered at that point. At this point now, I can keep ramping up a load and see what happened next. If you keep raising the load to see when another layer will fail. Let's do that. The reduction rule, let me double check. This is the reduction rule we're talking about. All right, so you basically, all right, so I forgot to do one thing. I need to reduce the new 1-2 as well. I didn't reduce that one. I forgot about this part. New 1-2 doesn't reduce. New 1-2 the same. New 1-2 didn't change. E1 didn't change. E2 change, G1 change. I did right. That's right. This is the reduction rule. Okay. All right, let's go back to the calculation. Let's keep raising the load. I'm at step 2 now. Step 2 is, what is that? Step 2 is the starting point of this. I'm gonna multiply stress. I'm gonna make it 4. What happens here? All right. All right, the highest is this one, 6.8. This is highest, 6.48, 4, 5.5. All right, it's over now. Let's do 5.2. That's pretty good. It's a pretty close one, 5.1. 4.15. Bingo. When the load growing from 2 to 5.16, I hit a spot where second failure occurred. Okay. That failure occurred. The indication is the Tsai Wu indicator reaches 1. Okay. And let's determine what kind of failure mode it is. Let me look at the individual failure indicators. All right. In this case, based on the maximum stress theory, what's high is the tensile stress in one direction. One direction tensile stress, this stress high. So this will be the tensile failure of the fibers. So as we said before, if a fiber break, usually they consider the laminates break. So we basically, at the end of the life, we have redistribution, and when we reach, this is when the scaling factor equal to 2, this is when the scaling factor equal to 5.16. At that point, we have a first fiber failure. That's usually taken as the end of life for that laminate. This happens for this particular laminate. If there are different kind of layout, different kind of number of layers, this person could keep growing a few times until it reach the condition that fibers start to fail. Okay. In my case, I just keep updating. If that needs another step, I would save the this state and then copy and paste another sheet and then keep calculating until I find another state when the layer fail and I reduce it. Okay. That's a general step. Of course, you can write this up into a program. You do all this criteria automatically using a code. I'm simply doing manually. I'm doing manual. I'm in the loop of the code. I look at the failure criteria, and I do the reduction in stiffness manually. You can do that automatically using your code, but that's doable if you good with coding. If you're not so good with coding, you can do it manually, like what I did with Excel. Okay. All right. Any question about this part? All right. The other thing I want to calculate, I want to go over today is the implementation of hygrothermal load, which is a key part of the CLT code, which I didn't ask you to implement before, but I will ask you to implement after exam 1. You want to put a hygrothermal effect into your code. So what you did so far is basically, what is the stress strain due to the mechanical load? You apply load, what is the stress strain? What's the deformation? What is the strain? What is the curvature? All those things. You can answer those. But as we discussed before, the reality is once you have the laminate fabricated, there are already pretty high stress built into them due to the thermal expansion effect. You cool down from the current temperature. The laminate could absorb moisture, and they could try to expand different amount. Different layer could try to expand different amounts, and that results in infights. So right after fabrication, the infights starts. You have stress built in. The true stress is your infight stress superimposed with additional stress with additional mechanical loading. So we gotta take account of that. Otherwise, your stress is not true stress. There's a missing part of it. I will just explain how I did in this code that I wrote in the Excel, and you can try to mimic the process and add this part into your code. Okay, that's the purpose of this. So I have this thermal stress part programmed in. I can point you to the blocks where I have this calculated. It starts from here. Okay. So I first assign each layer a delta T. In this case, it's minus 75 Kelvin. I assume the stress-free temperature is somewhere high. At room temperature is 75 degrees below the stress-free temperature. And then I also provided, this is a material property. It's a thermal expansion in one direction, thermal expansion in two directions. Okay, this is a material property. So I basically provide that for each lamina. They could be different, but in this case, I made everything the same. This is the thermal expansion in one direction. In this case, very small. Thermal expansion in two directions is much high. It's a 3 order magnitude higher than that. That usually is the case because the matrix, the polymer, expands a lot more than carbon fiber. Okay, so that's my input. Okay. All right, I want to explain again the formulas we need to use to calculate hygrothermal effect, which is over here. These are the equations you need. I'll upload this set of equation onto the Blackboard later today, so you can, if you're ready to do it, you can do it. You can calculate these things. These equations I have programmed in my spreadsheet. I have this all in. I want you to start programming yours after exam 1. So the rationale for calculating hygrothermal effect is this. This is a fundamental rationale. It basically says the total strain of any layer is the sum of 3 effects. The 3 effects are mechanical effect due to stress-induced strain. This is a stress-induced strain. Temperature effect, the second column is temperature effect. Third column is moisture effect. So your total strain you observe in the layer is the 3 effects added together. Okay. This is a fundamental assumption we need to make. Okay. Then you can rearrange this. So you can rearrange it. You can basically move these 2 column vectors to the left-hand side, and then you multiply the inverse of this matrix, you get this equation. It basically says if you subtract thermal strain and moisture strain out of the total strain, and you multiply the stiffened matrix, you get a stress. So these are the same. So this carries the same information as this. It just restate the same physical relationships. All right. And then the strain due to temperature effect is simply this. Basically, thermal expansion coefficient multiplied delta T. Okay. We assume the lamina is symmetric. So when you have thermal expansion, you don't have distortion. So this shear strain is 0. Same thing here. The moisture strain induced shear strain is 0 as well. In this case, we have moisture expansion coefficient time changes water contents, moisture contents. Okay. So I will just explain thermal effect. Moisture effect is very, from the standpoint of methodology, is exactly the same as thermal effect. So moisture effect can be dealt exactly the same way. If you know how to implement thermal, you can implement moisture. I didn't implement moisture effect in my code, so I don't have that program. I could do that, but I just implement this part. Okay. All right. So what happened if you observing the same effect instead of from material coordinate, you're observing from global coordinates? Then you have this relationship. This is basically the same story told at different coordinates, XY coordinates. You basically, your total strain on the left-hand side here is the sum of a mechanical effect, temperature effect, and moisture effect. Okay. All right. And then the temperature effect is proportional to temperature, moisture effect proportional to moisture content, and the material constants. Okay. It turns out that you can actually transfer the expansion coefficient from 1, 2 to XY coordinate the same as your transform strains. The same relationship holds. So if you put alpha x, alpha y, alpha xy, they follow the same relationship with alpha 1, alpha 2, and alpha 1, 2. Alpha 1, 2 is usually 0. Okay. So this is the same relationship of transforming alphas. With this, you can transform from 1, 2 to xy coordinates using this matrix notice. This is matrix equal to this. This is a utility matrix that you use as you transform stress. It's the same matrix. Okay. You can go from any direction you want. You can go from xy to 1, 2, 1, 2 to xy. Same set of matrix you used. Okay. And then you can calculate so-called fictitious hygrothermal load, which is nothing but the statement that the induced stress due to thermal and moisture effect is self-equilibrating. Assuming that you have laminated bond together, they're in fights, they're pulling different directions, so they have stress in there. But if you sum the stress from different layers, they will add up to 0 resultant force. They're self-equilibrium force. Okay. So if you apply that self-equilibrium condition, you arrive to this equation. This is a force equilibrium. This is a moment equilibrium. The physics of this equation is just equilibrium. Okay. Then you can calculate this. You can basically calculate these terms. N superscript T, which is a fictitious hygrothermal loads in terms of force. This is a fictitious hygrothermal load in terms of moment. And then you can plug those into. This is for moisture. Plug them into the same ABD formula. So basically, this says when you have these fictitious hygrothermal load, they are related to the midplane strain and curvature, just like your CLT equation. Okay. All right, but these are not a true load. These are not a mechanical load. These are fictitious load due to temperature rise, due to moisture change, right? Okay, then you end up with the same set of governing equation that relates your midplane strain and curvature, epsilon 0 kappa, with this fictitious load. If you're only considering thermal effect, you don't need this equation. You don't need anything with a C sub. If you only consider moisture effect, you don't need anything with a T subscript. Okay, superscript. Okay. This is with everything together. You have both temperature and moisture effect. You could only consider one. There are situations that you can you only need to consider one. Then you just drop the other term out. Okay. All right. The important thing is now you can calculate the midplane strains and curvatures. That would be moisture or temperature induced stretching and warping of the plate. If you solve this equation, You calculate these two number. These two number physically means the temperature induced warping and stretching. These two numbers. Now, NT and MT, NC, and MC are calculated from this equation right here. Okay. So you have delta T, you have apply thermal expansion. This Q bar matrix is exactly the same Q bar matrix you use to do your ABD calculation. Any questions so far? Are you guys with me? All right. So back to this equation, you basically calculate the mid-plane strain and curvature using the hygrothermal loads. The hygrothermal loads are not a true load; they're fictitious load. They're basically representing there's a temperature rise, there's moisture change, right? Okay. All right. And then you can use this calculated fictitious load-induced mid-plane stretching and curvature to calculate the strain in each layer using this equation. Okay. And that will be the total strain. Then you take the total strain, subtract the temperature effect, subtract the moisture effect, you get a mechanical strain. And then you calculate the mechanical stress based on the mechanical strain. In a way, we basically apply this set of equation reversely. We get this strain, we subtract this out, and then we multiply the inverse this, we get the mechanical stress. Okay. At that point, you have obtained the stress in each layer due to thermal mismatch or moisture mismatch. This will be the stress each layer due to moisture effect, due to thermal effect, everything will be captured here. And then this stress can then be superimposed with stress you calculated from other mechanical loads. Remember, this stress is not due to the true mechanical load, it's due to the thermal mismatch, okay? This whole logic is a little bit twisted. You gotta read this equation back and forth a few times to get used to it. Okay. Any questions? Now let me show my implementation. This is how I implement all these in my code right here. Okay. All right, so I basically follow the formulation. First, I want to figure out NT and MT. Remember, in my code, I only implement temperature effect. I didn't implement moisture effect. I mean, they're exactly the same methodology-wise, exactly the same method. So as you can see, each ply, I have n plies, k equal to n. Each ply contributes something to the fictitious load. Each ply has contribution. What I did, I basically calculate the contribution to n and m from each ply, which is over here. The contribution of ply number 1 to n is here. The contribution ply number 1 to m is here. M sub t is a fictitious moment due to temperature mismatch. This is a fictitious load due to temperature mismatch. I calculated for each ply how much they would contribute. I calculated just by using this equation right here, just using Q multiply alpha. Alpha is transformed from 1, 2 coordinates. My transformation occurs here. I have alpha 1, 2. This is in the material coordinate system, alpha. And then I have alpha xy, which is the transformation using the matrices, this matrix, transform matrix, which is the R inverse. No, here. This is the transform matrix. I calculated T and R, T transform matrix, T inverse, and this is the T RT R inverse. I basically use this matrix here to transform the alpha from 1, 2 to xy coordinate. This is transformed alpha in XY. Okay, and this alpha goes into here. Each layer of alpha. And I also have layer thickness. I multiply alpha to Q to layer thickness. I call this thing the NT. Also, I multiply delta T. I call this thing the NT contribution from that layer. Okay. Then I do this for all layers. This is the NT contribution from layer 1. This is NT contribution from layer 2, and this from layer 3. And I sum them up. I sum them up to here. This is the total hygrothermal fixed surge loads from all layers. I sum them up. According to this equation here, the sum, K equal to 1 to N, that's implemented in my code over here. All right. This is the sum of the moment load, the sum of the force load. This is my effectively hygrothermal load with contribution from all layers. Okay. Any questions? All right, then I keep following the formulation. I have NT and MT, sum them up. MT will involve H squared minus H squared. This is very similar to ABD building. So you gotta pay attention. This is H squared minus H squared, okay. Once I figure out MT, NT, I need to calculate. I need to calculate this epsilon 0 and kappa, okay, which is over here. This is epsilon kappa due to my this one. Actually, I calculate twice. This one. This is epsilon kappa due to my thermal load. Thermal load is giving at C18 to C23, which is here. So this is my epsilon kappa due to fictitious thermal load. All right. When I need to calculate thermal stress in each layer, I would use this column of epsilon and kappa back in here. All right. Then I can back to this slide. That basically is stress calculation here. No, strain calculation. I calculate strain first. Sorry, I calculate strain. Yeah, strain calculation first with the equation here. Then I subtract thermal strain out of it. Let's see where I subtract thermal strain. Oh, the second step here. My strain. Well, where did I subtract it? I couldn't find that part. All right, I need to look at this again. I think I might have made a mistake. I need to subtract. This is in-plane stretching plus kappa times the curvature. So that will be the total strain. Then I need to subtract. I need to subtract another factor. So I need to modify this. I don't think I might have made a mistake here. So So that is basically this. This is what I calculated. I guess I didn't quite come into this. I need to subtract this out and then get this and then calculate the stress, which is missing from this code. Let's see, stress. Right. So that's not quite right. So I need to update that. All right. Apologize for that. I guess I didn't finish that part. I will try to fix this, and I will talk about it on Monday again. See if that make more sense. So we're almost to the end of it. We calculate this, and then we just need to subtract and then multiply Q again, and to get this stress, sigma. That will be the thermal stress. Now you may ask, what if the case involve both thermal and mechanical effect? You would just superimpose the stress you calculate due to thermal and the stress you calculate due to mechanical. You sum them together. That will be the true stress in each lamina. You can calculate the thermally induced stress like this, and then you can calculate the mechanical induced stress using your current ABD current CLT, and the true stress is close to the. You add them up. You layer by layer, you add them up. That will be the. For each layer, you add up a thermal stress with mechanical stress. If there's additional moisture effect, you would calculate moisture induced stress, temperature induced stress, and then on top of that, you calculate mechanical external load induced stress. And the sum of three is the true stress each layer. All right, any questions? I will correct my code. I will produce some examples with the standard input so that we can check our results together. We can compare notes. So make sure that we have consistent code. Okay. Similar to the example I gave you before, I'll give you a set of examples calculating thermomechanical, hygrothermal stress. All right, any questions? All right, at the end, I want to say something about a exam on Monday. It will be a open book, open note exam. You don't need to. So we'll cover the CLT part, the failure theory, as well as the not the failure theory, just CLT part, calculate the stress, and also the micromechanics. All right. So that's what I will give you the exam sheets, and you calculate, and then you finish, and you email me your answers at the end of the exam. You use your code, you use your notes. It could be in the computer, it could be hard copies. I don't care. It's open note, open book exam. So you need to bring your computers with a working CLT code. That's most important thing. Otherwise, you cannot calculate anything manually. Any question about exam one? Any other questions? Have you all finished your code and compare it with the yes. Once you have a CLT code ready, it doesn't take very long to calculate. You just type in the input and you copy the output. I don't think time will be an issue. Yes. When for the homework that you sent me today, you want to describe the patterns. When you have a symmetric layup, when you have a quasi-isotropic layup, the ABD has pattern, certain term are zero. You want to describe those patterns. You can find those patterns out by experimenting. You put in a symmetric laminate, you look at which term are zeros in ABD. What I'm looking for is you describe the patterns, ABD in ABD when you have a certain symmetry in the layout. Is that clear? Did anyone have any problem with it with CLT or everyone finished your CLT code? Okay, if no more question, I'm gonna stop here. I'll let you enjoy your weekend. I'll see you guys on Monday. Have a good weekend.
Thank you.
All right, bye-bye.